Hello everybody, and welcome to our video on double integrals over general regions. So we talked about integrating over a rectangle R, and we gave a very precise definition for what that meant. So we would like to be able to integrate functions over arbitrary bounded regions. So the question is, can we, first of all? Is it valid to consider taking some arbitrary region, like this D here, and just integrate over it without having some sort of problems in the definition of an integral? And actually, yeah, it's totally fine, because we could always define a new function, cap f of xy, equal to little f of xy if xy is in D, and equal to 0 if xy is in R but not D. Then the integral in our rectangular region of cap f would have the exact value we want for this integral over D of little f. So it's totally natural to integrate over a, irregular region like this, even though our formal definition is in terms of the rectangles. So, definition: a plane region D is said to be of type 1 if it lies between the graphs of two continuous functions of x. That is, the region D is the set of points x, y such that x is between a and b, but each y coordinate is between a function g1 of x and g2 of x. So here, if we look at these pictures, we've got two curves, and the curves are bounded by a and b along the x-axis, and for any point x, y inside that region, for each x value, the y value corresponding will be between these two functions of x. So same thing here, right? Got some x, there's a y value, and that y value will be strictly between the two curves values at that point x. So here's another one of these regions. So again, these regions of type 1, x is fixed between 2 points, and y is stuck between two functions of x here. So if we have a type 1 region, then the way we integrate this is we write our double integral as an integral from a to b of the integral from g1 of x to g2 of x of the function f of xy dy dx. So by integrating with respect to y first, when we integrate, we'll substitute in these functions of x, and that will eliminate the y variable, so that then when we integrate with respect to x, we'll be evaluating at these fixed points, and we'll get an actual numerical value at the end of the integral. Now, definition: a plane region D is said to be of type 2 if it lies between the graphs of two continuous functions of y. So that is, D is the set of points x, y, where y is between two fixed values c and d, but x is between two curves that are functions of y, h1 and h2. So similarly here, if you take a point inside the region, you can always say that the y value is between c and d, but the x value is between these two functions of y. So whatever y is dictates that x is between these two functions evaluated at y. And so here's two other regions that are type 2. So for type 2 approach, we just change our integration order here, right? So here we integrate from a to b. That should be c to d. Yeah, let's fix that. Another typo, so that should be c to d. So the integral from c to d of the integral from h1 to h2 of f of xy dx dy. So again, we integrate with respect to x first. We're going to evaluate that antiderivative at these functions of y. So then everything will be in terms of y, so that when we integrate it with respect to y, we'll get a finite number evaluating at these endpoints. So more properties of double integrals. Well, if we have D can be split into two regions where D1 and D2 don't overlap, except possibly at their boundary, then the integral, the double integral over D of f, is equal to the double integral of f over D1 plus the double integral of f over D2. So in other words, if you're trying to find the volume above the whole region, it doesn't make a difference if you split the region into two pieces. That's perfectly fine. So we often use this property to evaluate integrals over regions that are neither type 1 nor type 2 by splitting them into appropriate regions. So this is an example of that kind of idea, right? So you draw a fixed x value here. So this would be from A to B. Actually, this curve isn't quite right. Doesn't make perfect sense here. From C to D. So here, what do we see? This D2 region is strictly between C and D on the y-axis, but you can't make such a straightforward comparison on the x-axis. So you would describe this as a type 2 region. And in this case, you can say, hey, the x values are strictly between A and B here. We've got these straight lines. But the y values, you got this kind of curve that messes things up a little bit. So you would call this a type 1 region. So if we have a region that is neither type 1 nor type 2, you split it up as appropriate, and then you'll have a region, multiple regions that you can evaluate separately. Okay, so another property is that the double integral of 1 with respect to the area just gives you the area of the region. So that should make perfect sense, right? This is like as if you're integrating a prism whose height is 1. So you got the area of the base times the height. That's just the area. So that's exactly what you've got here. And lastly, that if you know that f is bounded by cap M and little m here for all x, y, and d, then the double integral of f is bounded by little m times the area of d and big M times the area of d. So again, this A of d is the area of the base. So you're saying here that the volume, essentially, of this function's surface, the volume should be greater than or equal to its minimum value times the area of its base, and less than or equal to its maximum value times the area of the base. Okay, so let's go ahead and just jump into an example now. Evaluate the iterated integral from 0 to 2 of the integral from y to 2y of xy dx dy. So first we integrate the inside with respect to x, and that's going to give us x squared times y over 2, evaluated from y to 2y, dy still. Now when I evaluate x at 2y, I'm going to get 4y squared times y over 2 minus this integral at y, which will be y squared times y over 2. We're going to integrate this with respect to y. But first, let's combine it all together. So 4 over 2 is 2. So this is 2y cubed minus 1/2 of y cubed. So that leaves me with 3/2 y cubed. And we're integrating this with respect to y. So now this gives us 3/2 times y to the 4th power divided by 4, evaluated from 0 to 2. So that's 3 over 8, so 3/8 times 2 to the 4th minus 0. So 2 to the 4th is 2, 4, 8, 16. Divided by 8 is 2. 2 times 3 is 6. Done. So these aren't too bad. The only difference is that our inner bounds here are going to be functions instead of just numbers. All right, so now let's consider a problem where we've got to actually figure out this region here. So we've got the double integral over the region D of x cubed dA. So here, I find that it's really helpful if you draw these regions. So sometimes it's not truly necessary, but sometimes it really makes a big difference in making sure you understand the picture properly. So if we take here, x is from 1 to e, and y starts at 0 and goes up to ln of x. But ln of x, ln of 1 is 0, and ln of e is 1. So in this case, I think it's pretty straightforward what our boundaries should be. We've got our function, our values y. So when we look at x, y, x is always between these two fixed numbers, 1 and e. But for a given fixed x, the y value can be between 0 and all the way up to ln of x. So this one's pretty straightforward. So let's go ahead and set up this integral. So since y has our variable bounds, we want to integrate with respect to y first. And then we'll integrate with respect to x after. Now, if I integrate this with respect to y, I get x cubed times y. Evaluated from 0 to ln of x dx. So this gives me x cubed times ln of x dx. Because when I evaluate at 0, I'll just get 0 here. So now, this would require a integration by parts. So u is going to be ln of x. Du is going to be 1 over x dx. dv is going to be x cubed dx. And so v is x to the 4th over 4. So uv gives us ln of x times x to the 4th over 4. Minus the integral of v du. That's x to the 4th over 4 divided by x. So that's x cubed over 4. And the whole thing's evaluated from 1 to e. So this is ln of x times x to the 4th over 4 minus x to the 4th over 16, evaluated from 1 to e. And when we evaluated e, ln of e is 1, so this is e to the 4th over 4 minus e to the 4th over 16, minus everything evaluated at 1, but ln of 1 is 0, so this becomes minus 1 over 16. This is 4e to the 4th over 16 minus e to the 4th over 16. That's 3e to the 4th over 16 plus 1 over 16. So that's our final answer. Okay, so that's totally fine. I just wanted to illustrate, though, that we can actually re-describe this region in terms of a region with of type 2 instead of type 1. So let me show you what I mean here. We could have considered our bounds y from 0 to 1. Now, not all regions is it possible to switch, which is why we need to be able to do these both ways. But if I had instead considered my region from 0 to 1 on the y, and if it was from 0 to 1 on the y, then x would be bounded below by this green curve and above by e. So in that case, what's x? Well, if y equals ln of x, then e to the y equals x. So x would be bounded below by e to the x, and it would be bounded above by just e. So now if I wanted to set up my integral, I could set it up with respect to e first, or with respect to x first, I should say. And let's see how this works out. So here we get x to the fourth divided by 4, evaluated from e to the x to e. Then with respect to y. So this gives us e to the fourth over 4, and we're still evaluating from 0 to 1, minus e to the 4x, because it's e to the x to the fourth over 4, dy. That should be e to the y, not e to the x. What am I doing? So this should be e to the 4y. Okay, so since we're integrating with respect to the y, e to the 4 over 4 becomes y e to the 4 over 4 minus e to the 4y times the, divided by the, you have to do u substitution here, u equals 4y. You end up with du equals dy over, du over 4 equals dy. So we need this to divide by 4 again, so that should be over 16. Evaluated from 0 to 1. And when I evaluate at 1, I get e to the 4 over 4 minus e to the 4 over 16 minus 0 minus e to the 0, which is 1 over 16. And by golly, that's exactly the same answer that we got before. And I truthfully think this integral was a little bit easier to work with, but we had to make that first change into this other type of integral, which is a little more complex when you're dealing with functions as your boundaries. So just keep that in mind. These can be a little bit tougher. So choosing which way you're going to integrate can make a big difference. Can make the integral easier, but maybe it's a little harder to figure out how to describe your region. But also keep in mind that if you can't write your region in that other way, then you're not going to be able to make that change, and you just have to integrate it with respect to the variable first that you can. Okay, so with that out of the way, let's go ahead and move on to another problem. Evaluate the double integral over d of x squared plus 2y dA, where d is bounded by y equals x, y equals 4, and x equals 0. So I got to figure out what my boundary looks like here first. So we've got y equals 4 is an upper boundary. We've got x equals 4 is a boundary here. And we've got the line y equals x. So there's multiple ways we could set this one up, and I think in this case it really isn't going to make much difference which way we integrate with respect to first. But let's just consider a point. I think it's always easiest if you actually plot a point in here and think about its coordinates. So we want to pick one coordinate that is between two fixed values, and then describe the other coordinates restriction based on the curves. So here, what do I see? Well, I could do this as x is between 0 and 4, and y is between 0 and x. Or sorry, y is between x and 4. My bad. All right, so y's lower bound here is the line y equals x, and y's upper bound here is the line y equals 4. So I'm going to go ahead and just tackle it that way. So this becomes the double integral, and we'll be integrating with respect to y first on the inside, and then x. So dy dx here. And if we integrate with respect to y here, we get x squared y plus 2y squared over 2, which is just y squared, evaluated from x to 4 dx. Now here we're evaluating y. So if I replace y here with 4, I get 4x squared plus 16 minus, now we evaluate with, replace y with x, gives me x cubed plus x squared. So this is 4x squared minus x squared, that becomes 3x squared. And this is negative x cubed. And this is just a positive 16. Okay, so we integrate this like normal. 3x cubed over 3, which is just x cubed, minus x to the 4th over 4, plus 16x. And evaluate this from 0 to 4. This is 64 minus 4 to the 4th power is going to be, let's see, 4, 16, 64, 256 over 4. Plus 16 times 4, which is 64. And minus 0, because all of this will be 0. Okay, so this is 64 plus 64 is 128. Minus, now 256 divided by 4 is 64. So altogether, this is just 64. All right, that's it for that example. Let's go ahead and move on. Find the volume under the surface, z equals 1 plus x squared y squared, and above the region enclosed by x equals y squared and x equals 4. So let's just draw that out. We've got x equals 4. So if x equals 4, that means y equals plus or minus 2 here. And this thing looks like a quadratic facing to the right. Now there's a sort of tiny complication here, which is that when we look at these regions, we see that our y value is going to be bounded between these two different parts of the graph, but these are actually the same function. So that means we need to split this function into two, and we'll call one of them curve 1 and the other curve 2. So that would mean curve 1 here is x equals the, so I take the square root of both sides. It's going to be y equals the positive square root of x. And curve 2 here is going to be y equals negative square root of x. So now if I take any point xy, what can I say? I can say that x is between 0 and 4 from here to here, and that y is between the negative root of x and the positive root of x. Okay, so let's go ahead and try setting that up in our integral. So we'll want to integrate with respect to y first, then x. So this bound should be negative root x and positive root x here, and then 0 to 4. Okay, so if we integrate with respect to y first, we get y plus x squared y cubed over 3, evaluated from the negative root x to positive root x. And then we'll integrate that with respect to x. Okay, so here we get the square root of x plus x squared times the square root of x cubed. But the square root of x cubed is x to the 3/2 power times x squared is going to give us x to the 7/2 power. So I'll write that out in 2 steps. X squared times x to the 3/2 divided by 3 minus. Now we've got negative root x plus x squared. And here we're taking a negative to the 3rd power, so it'll still be negative. And it'll be x to the 3/2 again. Over 3. Square root of x plus the square root of x is 2 times the square root of x. But I'm going to write that as 2 times x to the 1/2 power. And now here we've got x squared times x to the 3/2. So that's 7/2. So x to the 7/2 over 3. Minus a negative, so that's going to be plus again, the same thing. So that's just 2 of those. And now I can integrate like normal. So this is 2x to the 3/2 divided by 3/2, but that's the same thing as multiplying by 2/3, plus 2/3 times x to the 9/2, but that's the same, we need to divide by 9/2, which is the same thing as multiplying by 2/9. And then we evaluate this from 0 to 4. So this is 4/3 times the square root of 4 cubed plus 4/27 times the square root of 4 to the 9th power, and then minus all of this evaluated at 0, but that's just 0. So this is 4/3 times 2 cubed, which is 8, plus 4 times 2 to the 9th, which is something. It's a little bit above my mental math abilities there. So 8, 16, 32 over 3. Plus, and we'll just call on the old calculator there. 2 to the 9th power, it's 512 times 4. So it gives me 2048 divided by 29. Now, this is a perfectly fine answer. I'm not worried about any common denominators or anything here. That's good enough. All right, so that's it for example 4. Now let's just take a look at one more little problem here. So if we look at this problem, if we try to integrate this with respect to y, we've got sine of y squared dy here. This, you may recall from Calculus 2, is not something that you can integrate. You would have to use like some sort of approximation approach or something, but you're not going to be able to integrate this directly. That being said, we could change our bounds here. So if we look at our region, so what does this region tell us? It tells us that y is between x and 1, and x is between 0 and 1. So if we try to draw that out here, x stops here, starts here, and then y is bounded above by 1 and below by the function y equals x. So any x and y coordinate will look like this. So I could re-describe this region by saying that x is between 0 and y is between 0 and 1. So let's see what that does to the integral here. Okay, so now when we integrate this, we're integrating with respect to x first. So we actually just get x times a constant here. So it's x times sine of y squared, evaluated from 0 to y, dy. And evaluated at y, I get y times sine of y squared. And evaluated at 0, I get 0. And now here we can just do a basic u substitution. U equals y squared, so du equals 2y dy. So du over 2 equals y dy. And if I evaluate u at 0, I get 0, and u at 1, I get 1. So I get new bounds of 0 and 1. They happen to be the same bounds. And I get sine of u du divided by 2. So when I integrate this, I get negative cosine of u over 2, evaluated from 0 to 1, which gives me negative cosine of 1 over 2 minus a negative cosine, which becomes positive at 0. But cosine of 0 is just 1, so this becomes negative cosine of 1 plus 1 over 2. And that's an exact answer, so you can leave it like that. Okay, so we got one more example here. So use property 3 to estimate the value of this double integral e to the sine of x cosine of y dA, where d is the disk with center at the origin and radius 2. So first I'll just draw d. And it says use property 3. Well, what's property 3? Well, if we look up, property 3 was the property that said the double integral is less than or equal to the maximum value of the function times the area of d, and greater than or equal to the minimum value of the function times the area of d. So let's take a look back at our function. Well, if we look at e to the sine of x cosine of y, the maximum values sine and cosine can take are both 1. So this can't be bigger than e to the first power, which is e. And the minimum values they can take is negative 1. So negative 1 and negative 1, which wouldn't work. So negative 1 times 1 would give you negative 1. So the minimum value this has to take is e to the negative first power, which is 1 over e. Now, if we look at d, the area of d is given by pi times the radius squared, which is 4. So that tells us that our double integral over d of this function is somewhere between e times 4 pi and 4 pi divided by e. Now that might be a pretty big range, but even just from a standpoint of checking your own work, This can be a helpful quick tool because if you're checking a double integral and you get an answer that isn't anywhere in between these bounds, then you know that you must have made some sort of mistake there. So something to keep in mind. You could use this as a tool for checking your work on occasion. All right, well, that's it for this section. So thank you for watching and have a great day.